Still going to look at a bit of terminology. I'm still going to use the same example we used in part 2. We toss a die and event A is getting a prime number. Event B is getting a 4. Event C is getting a 6. So we will refer to this example to help us. We have now spoken about independent events, complementary events, mutually exclusive events. Make sure you understand that. We're going to look at a few more words. One is the union, which we write with a little u but without its down line. And the union is the same as saying or, and we mean then, shall I say, both are acceptable. If the answer comes from one or from the other, then it's acceptable. So, I want to do a rule for union. Here's a general rule for union. And this is for any events. The probability of my solution coming from A or B, of my outcome being either from A or from B, is the probability of getting A plus the probability of getting B minus the probability of getting A and B. This is my general rule. In other words, it works all the time. And then I must just explain what we meant by this part. That is what we call intersection. And we say and when we write that. So then it has to come from both of them. So if we go back to our example here, and we include an event D, which was get an even number, then the intersection of A and D is 2. Let's maybe just do a few of these first. Intersection of A and D, which outcome lies in both of them? A 2. The intersection of B and D, round bracket, the curly brackets are your outcomes. What's in both B and D? A? 4. But the union of B and C, B or C in other words, is the 4 and the 6. So the union is throw them together. The intersection is which overlap. Your general rule counts for everything, whether they are independent events or mutually exclusive events. It always works with all of them. So that's our general rule for any two. And as long as you can see there are 4 terms in that equation, as long as you have the values of 3 of them, you can always find the 4th one. Right. If we have mutually exclusive what were they? They can't occur at the same time. Then their intersection the probability of both of them happening at the same time is 0. Mutually exclusive, their intersection is 0. Mutually exclusive, I'm making a mess here, and I'm not going to have space. Let's go here. The probability of A or B for mutually exclusive is then just the sum of the two probabilities. And if you refer to our general rule, you'll see why. Because for mutually exclusive, this last one will be a 0. So that's why your general rule is good. It works for all of them. Right. There's one more for independent. For independent events, the probability of A and B, and I'm not really referring to my example, just a general A and B, is the probability of A multiplied by the probability of B. So notice the difference between that one and that one. This is usually a way, if we already have the probabilities, is a way of checking if they are independent. So if I told you nothing, I didn't tell you what the experiment was or anything, I just told you what the probability of A is and the probability of B, and I tell you what the probability of the intersection is, then you can see if this thing is true, and that will tell you they were independent events. If it's not true, then you will say no, they were not independent events. Again, all these rules very, very important.